Good evening, everyone. My name is Naomi Balabudro, and I'm the CEO of the Deep River Public Library, and I am delighted to welcome you this evening to what promises to be a fascinating discussion. Many thanks to CNL for partnering with the library to host, to Bolu and to the team here, as well as Ellen and Alice for bringing forward all of these ideas. We are thrilled to work together to support really unique learning opportunities in our community. To that extent, we are also excited to provide a slight teaser that in celebration of Ontario Public Libraries and Nuclear Science Week last week, in a couple of weeks we will be launching a joint initiative where CNL supports us with a 3D printer for the community in the library, so keep your eyes out. We are so happy. I would like to start by recognizing that we gather on the traditional and unceded territory of the Algonquin Anishinaabe people. We honor the rich history of the Anishinaabe people on this land and work to include and celebrate Indigenous knowledge and stories in our collections and our library services. As we look towards the river where Algonquin families used to live, we strive to provide opportunities to learn together as we journey towards truth and reconciliation through including books in our collection and speakers as part of our services. A few housekeeping items. You may notice that the elevator is under construction, but so it is not usable at this time, but we are very excited that it is under construction. In case of emergency, if you need to use stairs, please make your way to the main stairwell and we will help safely evacuate from the building. There is an emergency exit just outside that door and to the left, and the washrooms are behind this wall in the hallway. We have coffee, tea, and cookies always, and we hope that you will stay to continue the conversation after our panel. It is my pleasure to introduce Ashlea Colton, Acting Manager of Program Review for the Advanced Reactors Directorate. Ashlea has over 14 years of experience at CNL in reactor physics analysis and computational sciences, and she has served as the Program Review Manager for the Advanced Reactors Directorate since February. She has extensive experience leading complex computational research projects and oversaw the procurement, acquisition, and installation of CNL's newest high-performance computing cluster named Athena. She also co-organized the first Canadian Nuclear Society's Conference on AI and Machine Learning in 2020 and continues to champion the integration of computational techniques in all aspects of research at CNL. I will pass it along to Ashlea.
Thank you for that introduction, Naomi. And thank you for thinking of this panel and for thinking of inviting CNL for this opportunity. We love to get a chance to get it into the community and talk about the type of research that we do. So I just wanted to thank you for that. Am I talking close enough to the microphone? Okay. Oh, okay. Cool. Better? Okay. Got it. All right, so AI in nuclear, it's a very exciting topic. I think I'll first just indicate we have 3 panelists here today to answer questions at the end of this session. We're going to go through a series of introductions for these panelists where they will discuss their background in the nuclear industry and how that aligns with their experience with artificial intelligence and machine learning, so you have a bit of an idea of the types of questions they would be able to answer for you. So I think that that's kind of important. So first off, I will do a little bit of a background on myself before we go through each of our panelists. If my mouse works. I'm clicking in the wrong place. That's what happens when you're. Yeah, I gotta click here. Haha, excellent. Me. All right, so I have a bachelor's in nuclear engineering. Naomi covered most of this. So basically, I've worked on reactor physics modeling at ACL, then becoming CNL since 2007. And I've had the privilege of serving as a branch manager from 2000 to 2024 with a section in that branch, which was called Computational Techniques. And it sits within the Science and Technology portion of CNL under the Advanced Reactors Directorate. It was very focused on modeling and simulation, and the section that was focused on machine learning tended to pull in a lot of very interesting problems in research. So essentially what would happen is that being the branch manager for that branch, many people would be coming to me to ask, like, is this a problem we could use machine learning for? So it's a very interesting position to be in because some people are getting very excited about this type of technology, and to be the outward face of that, you start being able to help people figure out what types of problems we can solve with this technology. Okay, let's see if I can push the right button this time. Excellent, excellent. So, of course, like what are some typical or accessible examples? So the things that I wanted to draw attention to are image recognition type problems, because I find that these ones are the ones that are the easiest to understand from the get-go. So we can use machine learning to support ourselves in answering questions that answering questions that humans could probably normally answer, but we might want to do it faster or a little bit more accurately. And in this case, we were supporting the chimney swift effort. So we know that chimney swifts are a threatened species, and they are roosting in the stack at NPD. We need to monitor the behavior of these swifts. So there's actually a camera that's pointed at this stack, collecting data constantly for if swifts are entering or leaving the stack. And normally there is someone who's paid to essentially count the swifts. Are they coming in? Are they leaving? What is this behavior looking like? And we report it to the appropriate environmental authorities. What we supported using machine learning to do was to use image recognition, machine learning type technology of this video to be able to essentially count when these swifts are entering or leaving the stack, to be able to generate a running total. So I thought that that was a particularly interesting application and something that's a little bit more accessible. Additionally, on the left side here, it's some microstructural images of zirconium, where, so in nuclear reactors, the types of materials you use inside the core are pretty important. You want to make sure that they are fairly neutron transparent. So what that means is it's not gobbling up all the neutrons in your reactor, because if you choose a material that eats all of the neutrons, your reactor is not going to be very efficient, and it's going to be quite expensive. So you want to make sure that you're using these types of materials. So basically, when you're irradiating zirconium, it can cause different types of microstructural defects or things that you don't really want in that zirconium. It can, make it a little bit more brittle or behave in a way you don't want it to behave. So we use these microstructural images to monitor the state of that zirconium. You take different samples, you take images of those samples, and it tells you sort of what's going on in that material. Normally, humans would be outlining these different sort of defects or different phase changes in the material, and it takes quite a bit of time, as you can imagine, to try and just carefully outline each individual component. So we were able to use machine learning techniques and image processing techniques to quickly be able to kind of categorize these different phases within the zirconium itself. And basically, if you're using machine learning in this way, you can enable yourself to be much more, like you can enable the process to be much more efficient, but the human is still in the loop to be able to verify if what you've done is correct. You're not putting like a machine in charge of anything important, right? So I thought these were two like excellent examples. Okay, one second. All right, so. All right. Now I'm happy to introduce Reeghan Osmond, who is a fuel research scientist in the Advanced Fuels and Reactor Physics branch, also in the Advanced Reactors Directorate, where I work. Okay, perfect. Reeghan? Hello, everyone. All right, so we'll get into what I do here. So essentially, I do image stuff. I do things with computed tomography, which people may know from hospitals as CT scanning. So essentially, we'll have it's essentially like when you go to the hospital and you need to get a brain scan or something like that. It's used to look inside of somebody without having to cut them open, I guess. So I kind of call that non-destructive testing, but I don't work on humans, so maybe that's, I don't know. I don't know if doctors do that too, but yeah, essentially we have an X-ray source on one side and then a detector on the other, and they spin around the person and they take a bunch of X-ray images. I do a similar thing, like I said, not on people. And those are used to do things like I said, make a brain scan. So essentially from these X-ray images, you can kind of look through everything in 3D, and you can look through and see, okay, is there an issue inside of the person's head? For me, I'm looking for things inside of fuel or components. And one important thing to note is that based on how high of a density the material is or the atomic number, it'll appear at different shades of white, basically. So it'll be black if it's like air, so low density, and then higher density or higher atomic number is going to be white. So you can see here there's like bone all around the edge, so that's like higher density, and then the brain is slightly less dense, and then there's air around the head. So yeah. And then specifically, I'm working a lot on advanced reactors because I'm in the Advanced Reactors Directorate. So we have this fancy new reactor that might be deployed sometime in Canada. It's called a very high temperature gas-cooled reactor. And essentially, it has this interesting fuel that basically it'll come in two different types. So they're kind of this size, but inside of them is what I look at for the most part because I'm doing non-destructive testing. And so inside of these parts here, you'll find these little teeny tiny fuel particles that are only about 1 millimeter in size. So they look like poppy seeds, but they're actually fuel on the inside, and then they're layered with protection on top. So each individual particle is self-contained and individually protected. So if one kind of fails, only that one will fail, and then there'll be a ton of others that are completely fine. And they're super resistant to all sorts of things, like high temperatures, all sorts of stuff like that. Of course, the reactors we have now are incredibly safe. So these are just another way of doing it. And we can also get higher temperatures. So at the end, when the gas comes out of the reactor, it's already really, really hot. So you can use that directly in a process. Instead of converting it to electricity and then converting it back to heat, you can take the heat directly. Yeah. So specifically, these are the teeny tiny particles that I look at. So this is just a cross section of it. So I can see the whole thing in 3D. And it has these different layers, like I said, and then in the middle it would be the fuel, and the different layers are just to protect it. So I'm basically looking to see how are those layers doing? Like, are they cracked? Is there a hole in them? Things like that, so I can look inside of that. And then, like I said,
don't worry, I'll get you there. There you go.
Thank you. How I use AI or like image processing is trying to identify those layers. So I can see them with my eyes. There are very distinct layers, but what would be really good is if I can see it all in 3D, I can see it in 3D, but also labeling it in 3D. So saying, this is the outer layer, this is the inner layer, things like that, because it's really important to see specific layers, how intact they are. So if I can label them and say, okay, this is the second layer in, and there's a huge crack in it, I know what could potentially happen through that process. So basically, I have to kind of label it myself, and then I give it to AI and train it, and it uses basically pattern recognition to find which layers are which, and then through that, I can essentially keep track of how these particles are doing. Yeah, thank you. Thank you, Regan. Okay, I'm happy to introduce next Rosa Ortega. She's a research and development scientist in the fluids engineering branch. In the, what do they call fleet director?
Reactor, fleet directorate, existing fleet directorate.
Yeah, in the reactor fleet directorate.
They changed it so
I know
far.
the name.
Yeah.
So fun.
I just. Okay. Oh, sorry. You just have to click.
That's okay. Okay, sorry. Hello, as Ashley said, I'm Rosa Ortega. I work for a fluids engineering branch for the existing fleet directorate, reactor fleet directorate. So basically what we do in this directorate is to keep the reactors that already are operating in Canada going. Yeah. So that's our main objective. So I specialize in can do primary heat transport pump seals and nuclear valve qualification testing, performance, and forensics. So traditionally, the primary heat transport pump seals are run to failure, or they are replaced when they're scheduled to be replaced. Valve maintenance is similarly. It's time based, so you don't do the maintenance or switchover activities based on the condition of the component. Just you set up a schedule and you do it when it's due. So with there are a lot of instruments that already monitor these processes, especially for the primary heat transport pump seals. Like we monitor pressures, we monitor vibrations, we monitor temperatures, but this gives you some warnings that things are happening, but commonly is not timely enough for you to react and do a planned outage on them, or to plan a switchover in the case of reactors that have multiple pumps. And so with AI and ML, we can analyze live data like vibration, temperature, friction to detect early signs of degradation. So the idea is that you teach the algorithm what does normal operation means, and any deviation that comes from there, it gets flagged. And hopefully you have like an inference engine that tells you for this, if these things are happening to your outside your normal baseline, this means that this problem is starting to originate. So like this enables inspecting and servicing only when needed. So you're gonna inspect, for example, the valves that really need your attention. You're not just gonna get the population that was due that day. You reduce worker dose because you don't need to do as many unnecessary inspections. Extend component life because you can have an idea on when these components are gonna fail and what to do to try to repair them before it's too late, and improve system reliability. So this really shifts from reactive to predictive maintenance, and it allows you to anticipate issues before failure happens. So I guess in the images that I have here, the first one is an illustrative image of a CANDU reactor layout, and the pumps that I'm referring are over there. The coolant pumps, the primary heat transport pumps, and the seals, basically what they do is prevent the heavy water to come out. So that's the easy explanation. And like on the second figure is in an image of a motorized valve, and these ones are usually used for isolation, and they don't get actuated very often. But when they get actuated, they need to really work because something is they need to isolate whatever is happening, right? So monitoring these ones it's pretty important. Oh, I don't know what I need. Sorry. So I'm just gonna give you an example of the kind of work that I do. So again, like this is for the primary heat transport pump seals. Again, like these ones prevents the heavy water to come out and allow the shaft to rotate under high pressure and high temperatures. And these seals need to leak a little bit so they keep lubricated. And that control leakage makes them last longer because reduces wear due to the lubrication and promotes efficient reactor operation. So the PHT pump seal issues are a source of forced outages in CANDU plants. If one seal fails, like usually you have several stages of the seal cartridge, but if they fail, then you have to shut down your reactor and you're losing time of operation, right? So the pump seal conditions that may lead to failure can be difficult to timely assess with the traditional methods. So looking at this in 2019, CNL started to work on ML-based condition monitoring for pump seals in CANDU units. And to do this work, what we use is the apparatus that you see in the image. So that's like a full-scale stuffing box for where the seal is placed inside, and we just run the seal in normal condition, and then we simulate failures, induce failures, and that way we can have kind of like a signature on how a failure is produced, and that way we train our machine learning models, and that way we can develop tools to assess if these failures are starting to originate in the reactors. Yeah, I think it's good. Yeah.
Rosa, which part is actually the seal cylinder in this image?
So this is a stuffing box. So the whole box is the stuffing box that connects the motor and the pump. The pump will go in the bottom, and the motor will go on the top. And inside is the seal cartridge.
The whole length of that metal cylinder?
So in this case, you have a shaft, and you're gonna have a bottom seal just to prevent the water not to come out, and then a two-stage cartridge usually is what is used in here. So in this case, they're 8-inch. We use an 8-inch shaft diameter.
Thank you.
Okay, great. Okay, so last but certainly not least, I'm happy to introduce Dr. Catalina Anghel. She's a computational research scientist in the computational techniques branch, where I was branch manager previously, also in the advanced reactors directorate. Okay, and she's going to also give an introduction to AI and machine learning and how it works. So I'm happy to get that overview as well.
Thank you. So yes, like Ashley said, my name's Catalina. My background educationally is in mathematics, but then I got interested in machine learning after my postdoc, and actually started as a student with Mr. Wills here in working on scintillation detectors in 2001. But then I went away and then came back and found that I love it here. So I came back after a while. So I was asked to give a primer on AI, and this will be very general. I just thought there are lots of terms that seem that might sound similar that have been thrown around, and there's a lot of hype. So I wanted to go in the first part over different terminology, the different types of machine learning, and what do we mean by data-driven models, because there's some overlap in the methods that were used in the past. And I was going to do, if I have time, a history of neural networks, but I'm going to put my timer on if I figure out how. Just because I want to make sure there's enough time for the panel discussion, so I might not cover too much of that. So what is artificial intelligence? So artificial intelligence refers to the systems which use data to achieve goals mimicking human intelligence, and that's the broadest field. And it includes rule-based methods. So for instance, in aviation, if you're correcting the flight, that might be a rule-based method, like the nose is too low, move it up. So it's automatically doing something, or it's making a decision, but it doesn't necessarily include machine learning. When you're talking about machine learning, this refers to methods which learn from data, and these can be methods that are very old, like linear regression, or can be more recent methods like neural networks. And deep learning, which are neural networks that have multiple layers that are more complicated. And when we, in nuclear science, it's these fields that we work most in. However, recently there's two fields that are very popular in culture, so I thought I'd touch on them. So it's basically, I went away from maternity leave, came back, and generative AI was huge. So generative AI refers to the subfield of AI where neural networks generate text, images, videos, music that often resemble real world examples. And so like ChatGPT got really big. And I can't go away from maternity leave, come back, and now the recent research is on agentic AI, and this refers to the subfield where autonomous systems make decisions with minimal human intervention. We don't do that in CNL, just don't panic. There's also some of the methods that come from other fields, like from statistics, which refer to the mathematical interpretation of data, especially in the context of uncertainty. So like linear regression is a type of model from statistics, and also from data mining, which is the analysis of large data sets to uncover patterns. So I hope this helps a lot, a bit to explain the different terms. And there are three types of machine learning. We mostly deal with the first two. So in the supervised machine learning, we give the model an answer. So we can say in the little robot, it's like, this is a cube, this is a cylinder, here's this one is a sphere, and then when it has a new example, it's already seen a lot of labeled examples and can classify it. In unsupervised learning, the model tries to cluster things based on similarity, for instance. So if you think of a child, they don't necessarily, if you say which image is not like the others, or can you put these images together, they don't necessarily have to have a label for that image. They can pick out which one is different, or like cluster them. So that's what we mean by unlabeled. They don't need to know that's a cylinder, that's a sphere. They just say, oh, all of my balls look similar or something. And those are the two that we mostly deal with. But there's also reinforcement learning, where the model tries different things and gets a reward or not. So again, if you think of kids, if they're trying to put the object in the boxes of different shapes, they will try many times, and then they're like, oh, it worked. And then they try again many times, and then so they get a reward from having it work, and they learn that way. This is a more cynical example of the robots, where one says the supervised is, they gave me so much to read and so many tests, and the unsupervised said, me too, but at least you got told the answers. And the third one, the reinforcement, says, at least y'all don't have to make your own book. So to give more concrete examples, so here, as I said, supervised models are trained to learn using labeled data and to approximate the relationship between inputs and desired outputs. So two types are classification and regression. And the image there is an image of classification, where you have a human subject matter expert who labels some of the images as a broken widget and some that are not broken. And then from seeing so many images and learning a pattern, the model can then label a new image. In unsupervised learning, there's two types, clustering and dimensionality reduction, and here the models are trained to identify patterns of similarity without being given labels. So there, in the example, you have, say, many images, and then it's trying to cluster the images that are similar. And so I guess I wanted to say, in Reeghan's example, she said she used a supervised learning if she tells, like she outlines the models in the layers in some images, and then when the model gets a new image, it can learn that way. The last one is reinforcement learning, where a model learns to perform a task through repeated interaction with an environment that's sometimes a simulation environment. So examples are the robot navigation, managing power consumption, or ChatGPT uses reinforcement learning from human feedback. Like a human might say, no, you got it wrong, try again, or something like that. And this is my only mathy slide. So if you hate math, you can just ignore the next minute. But I thought for people who like math, this is a good example. So how will we look at the same problem differently under statistics or machine learning? So in statistics, if you looking at biological data, physical data, you used to say, oh, putting the points, plotting the points x versus y, x versus some outcome, and say, oh, they look like a line, I'll fit a linear regression, and here is my model, like my linear function, and here's some metrics that say this is a good fit. So that's what you would put in a paper, or you would do for your stats homework. When you're thinking about machine learning, what you do is you wouldn't use all the points you're given. You take a subset of points, most of the points, like 80% of the points. Those are the blue points on the right-hand side, and you'd put those, you'd fit a model just to those points. And then you would take the points that you haven't yet fit and see how well, what are the errors for those points in the model. So you have root mean squared errors. You have some error on your training data, and then an error on your test data. So in machine learning and supervised learning, of key importance is prediction of the performance on a test set. But what is similar in both cases, and why this is a data-driven model, is that the parameters of the linear model are obtained or learned directly from the data. It's not that I come and say, I know the slope should be 2. Let's see how well this data fits to the slope of 2. It's more that the model is learned from the data. Do we have time? Oh, okay, I'll do the first slide and that's it. But I wanted to talk a little bit about neural networks because they're so popular right now. And they didn't really start, they started quite a while ago, like the work in building them. So in the 1940s and 1950s, people started building what is called a neuron, or these small functions that are the components of larger neural networks now. But and this is called the first golden age, from up until 1969. And what happened in 1969 is they said, well, these are very nice, but they can't model an XOR function. There's no way to divide this with a line. So that you put the blue points together and the red points together. And so people are, oh, they're not really that powerful, funding is decreased, so on. So it's this nuclear, first dark age or nuclear winter, AI winter. And then what happened is they kind of learned how to train a neural network. So they learned how to, if you have inputs and outputs, how to find the pattern between the inputs and outputs so that you get good results, and that's the backpropagation algorithm. So that improved the funding for a while and let more people do a bit of research, but then there were issues with computational demand of these, and also there are issues with, there was something, they were hard to train even with this algorithm. So there's the second dark age happened where again there's less research. And what started it up again basically was better computational hardware and better structures in the neural networks and ways to train the neural networks so that they trained better. And AlexNet in 2012 was the first that really got quite close, maybe I do have AlexNet that I'll go to here, but it's much more complex architecture, but it's a way to classify images. And you can see AlexNet in 2012 had an error of 16%, which was dropped the error from before by 10%. And within 3 years, the error exceeded human performance. So that's what started the third golden age, which is what we're in now. I hope that, I tried to keep it to 10 minutes, but I hope that helped explain some of the overview. Right.
It's fine. Okay, great. Thank you, Catalina. So we're done the presentation portion, and we're going to move into the panel questions. I have some prepared panel questions that I was going to ask, but after we do the maybe first 3 questions, we'll start entertaining questions from the crowd. That's great. Just a moment for AV things. Yes, excellent, that works. Okay. We just have to figure out. We're basically in this piece. All right, so the first question that I was going to address to Reeghan is, what are some promising applications of artificial intelligence and machine learning currently being explored at CNL?
Thank you. So of course, I don't know everything going on at CNL. There's so much going on. But I think that I've heard a few different things. So first, of course, is the stuff that I'm kind of working on, which is like imaging related or inspection related. So basically trying to speed up like processing of data and images. I think I've heard of some other things, which is very interesting. Like we have a lot of data, a lot of reports at CNL. So trying to use AI to kind of sift through all those reports that we have and scientific data and stuff from a lot of very important research that's been done over the past however many years, and actually trying to use it and learn from it. So like with the next generation of nuclear science coming up, there's a lot of stuff that we don't know and a lot of stuff that other people have done a lot of work on. So I think those are 2 major things. And I've seen some other cool things. So for example, like what Catalina and her team had worked on before, which is identifying basically for safeguards purposes, identifying, you can kind of give a signature or figure out a signature from fuel or something like that based on how it looks, or perhaps like what kind of signal it gives off. Maybe it could be a gamma spec. And you can kind of identify where those might have come from, like where did that fuel come from, stuff like that. So it's really good, essentially lots of pattern recognition things. Anything that we can do ourselves, but that is really annoying and we don't really want to do, I think is a good thing. Yeah, thanks.
Sure. So yeah, like I have several projects where I do condition maintenance, as you saw, like of primary like pump seals and valves. So I guess the objective here is just to using our test rig, and also we have used simulator data. Like there's a Candu 6 simulator in Fredericton. That's another branch that lives over there. They have a simulator, so we can produce synthetic data, and with that try to train our models, and also use test data from the test rigs, and then do some comparison with real data that the stations provide, and see how generalizable our models are. And yeah.
Okay, great. All right, so for the next question, what are digital twins and how do they help scientists and engineers use nuclear systems safely? This is for Catalina.
So digital twins is again, it's a bit of a new term for something that maybe happened before, but it's a mixture of machine learning models as well as physical models, and the goal is to model a component or a part or a whole, like say engine or something, or a reactor or a valve in such a way it's often related to real time, so that you are getting signals in real time and can update the digital twin in real time, and you can also try to test out what is happening, like if you want to adjust something in the component, what would happen if you would do it by simulation or using a machine learning model. So it's a way of trying things out before you actually apply it to the real component.
Yeah, awesome. That's excellent. And another cool example is that I know that they've used it at several stations before to kind of have technicians basically do operations that would constitute retube, which is a part of refurbishment, using equipment and simulations in advance of actually performing a lot of the retubing activities, thereby making it safer and more efficient. Not a CNL thing, but research that exists out there. Okay, so let's move to the third question. How can artificial intelligence make nuclear technologies safer, more efficient, or more reliable? This is for Rosa.
Again, with these models, what we're intending to do in conditioning monitoring is to see that something is going to happen before it happens. So these components are especially pump seals and some of the critical valves, they are already instrumented, but the data is treated as the operator just reacts when some alarm has been triggered. So sometimes you don't have early indications that something is happening, and also you don't have a very holistic approach of all the sensors that are measuring different things. So with these models, you can provide the idea is to provide the operators dashboards that can tell them okay, this is likely what is happening, go and check these areas, and that way make it more efficient and safer, and yeah.
Yeah, and just to follow up, nowadays there's a lot of digitization in the reactors, and so you have a lot of data, but it's hard to sift through all that data to look at the signals. So that's where the dashboard comes in. And to follow up on what Reeghan said, but there's also applications in nuclear forensics, so or in nuclear safeguards. So for instance, I worked on using imaging methods and to try to track triso pebbles, try to find a method of tracking triso pebbles and identify them as they cycle through, so that they haven't burned up too much, or no one's stolen one in their pocket or something. Not sure if that happens, but yeah. Or trying to find the signals of something that might happen at, if they're trying to detect from spectral signals.
Perfect. Thanks, Catalina. Okay, so those were our first 3 prepared questions. I'm just ready to take some audience questions if there are some. Okay.
Can AI currently, or maybe in the future a bit, be used to speed up problems like core optimization? So for example, can you PHWRs, fuel the reactor with natural enriched SEUs, thorium, plutonium. If you have certain economic goals, you want to get a core that optimally meets those. At the moment, there's a huge amount of thermal hydraulics, physics, fuel analysis needed on each and every core that's looked at. So it can be a very time-consuming process to get to an optimal core.
Yeah.
Is AI, can that be used to speed up this process and limit the amount of effort that might be needed?
Yeah, so another good question. I don't know if anyone else feels comfortable answering other than someone with reactor physics experience. No.
I think they are doing something like that. I don't know if it's for the. I might be wrong, but because I haven't read her memo yet. But I think someone is looking at this, but not for the current reactors, just for core optimization for micro reactors. Because maybe this could be very wrong, but like I think the idea is to use this AI as a surrogate model. So use AI just to, if you do enough simulations of the TH physics, etc., and maybe put in economic constraints, you can do simulations like that and just use machine learning methods to say, these are my inputs, this is what I get for the outputs from the codes, and then run it, and then it can repeat on new inputs that you don't have to run the codes for. Does that make sense?
Yes, so it's sort of cutting down the amount of
Yeah.
time-consuming code running, which
Yes.
is the core of what I was getting at.
Yeah. So I think we are looking at that, but not for the can-dos, just for smaller things, because they're easier to start with.
Yes.
Yeah, and also like we're the advanced reactors directorate, so we're looking at advanced reactors, right? There may be other groups kind of looking at that piece too.
My question is like, have you faced, like, what is the challenges that you have faced when when you implement machine learning or AI models? Like, I'm interested in that for so many projects that I currently have at CNL. But it's like, what are the challenges? What should we be considering? Because there are like a lot of data. We always talk about data, but then like not always works. So, what is your experience with that?
Yeah. No, I just didn't know it was here so quickly. Really good question too. You guys are very smart. So for me personally with imaging, I would say like the biggest struggle is actually labeling the image properly, because as Catalina mentioned, the way that I do things is I have to color basically or find a way to label every single 3D pixel in my image properly so that I can train the data so it can learn. So that takes a really long time. So that's why I'm trying to use AI, because it takes so long for me to actually accurately, properly color everything. And so essentially doctors do that too. Like, I don't know if anybody's heard of like the CT images that are able to predict cancer and detect cancer way better than doctors can in a quick time. So doctors have spent like hours and hours coloring and painting things and properly labeling things. But yeah, it takes a really long time, and nobody can just do it. You have to have the right person kind of doing it too. So yeah, but after that, hopefully it becomes worth it. Yeah, at least.
So for me, it's the quality of data too. Like I work with a lot of like data coming from test rigs and from stations, and it's not good quality sometimes. Like you get noise, you have periods when you don't have data, somebody disconnects an instrument and then plugs it in again, so you don't know what happens. So like cleaning up the data, we spend a lot of time like highen up that the data quality, and also like because like when you're working with station data, you have a vast amount of data, but sometimes it's poor quality, is not labeled. So if you want to do like supervised learning, it's a headache, right? So it's not properly labeled. You don't know what are the normal operation parts, the faulty parts, and also is not well balanced, right? Like for doing supervised training, you need examples of something happening, a bad event, and good events. And it's good that in stations in Canada we have normal operation, but like for machine learning, it's really hard to get those examples, and that's why we do a lot of like a test rig experimentation to create that faulty data.
And there's also the expectation sometimes. People say, we have so much data, but it's like if you're trying to predict something during a shutdown, maybe you have lots of data per shutdown, but you don't have that many shutdowns. And so then you can't, like every shutdown is one observation really. So it's called the low N high P problem, where you have lots of variables, but not many observations. And so you have to, if you give it to it doesn't, and there's not magic, like people are like, here, find something, but the machine learning algorithms are just like mathematical methods at the end, or approximations, so it's not necessarily that they know which is the important variables automatically. So I guess it's that. And
Thank you. Okay, any other questions from the crowd? Oh, we've got lots.
Yeah, I was wondering if you've been using AI to help in inspection campaigns of the current reactor, things like any kind of inspection of fuel channels. I believe there's a lot of manual monitoring, of signals while you're doing it.
Yeah. I'm not sure. I think we have to know more about the problem, right? Or do you know?
I know that the inspection and monitoring technologies branch is working on that. Like, I don't have the details, but I think they have like a Connexus project on reduced outages where they are looking at yes.
Yeah, I also don't know for sure about that too, but I do something similar where I'm looking at fuels or reactor components, like I said, non-destructively, to see, if there's any holes in them, cracks in them. So I can definitely say that AI would be very useful in at least flagging potential issues, and then the person can come and say, oh yeah, that's definitely a problem, stuff like that. Of course, all done with people so that we can double check, but at least in that way you can kind of automatically analyze things a little bit faster. Yeah.
Next question?
Oh, yeah. No, I'm loud. So yeah, when you're doing the machine learning, looking at things like the pump seals and things like that, do you find that the patterns it identifies are easily explainable in retrospect, where you can look at it, you can say, oh wow, yeah, it's always this one sensor that it's using to flag, or are they kind of obscure patterns that still don't make sense even when you know they work?
So in the case of like pump seals, like we're trying to make the models very explainable. So what we're using is transfer functions between the electrical signals that we get from the instruments, like temperature, pressures. So it's very explainable from a control perspective, right? We're trying to teach the models the dynamics of the system. And for example, we run like a number of hours of normal operation, and that gives you a cluster of like poles and zeros that are from your transfer functions in control theory. I'm sorry, I'm getting too technical, but like it's very distinct, like that distribution, when you have an anomaly happening. Like for example, when the seals are rubbing together, the cluster is in another place. So that can be explained with control theory and also with statistics, because you can see the shape of the distribution is very distinct from one to another.
And this is a big, in general machine learning, explainability is a big research topic recently because it's needed. So for instance, for images, nowadays a lot of papers highlight, as Reeghan said, the portion of the image it is in some sense looking at. So it isn't quite as, it doesn't mean that the neural network is actually looking at that image, because there's already a layer of abstraction there. What do you mean by looking? What do you mean by, there's mathematical methods used to look, to sort of quantify that. But yeah, there's more research into how to make the methods more explainable, or at least, yeah.
Thanks, Catalina. Thank you. Okay, next. Any other questions from the audience? Oh.
Okay. Oh, this is here's a short question for Rosa. To the extent that you're allowed to say, have any of the utilities yet adopted these predictive methods? And if not, how far into the future, or what are the challenges to get them adopted?
Okay.
So yeah, we have several projects with the utilities, and for the specific case of the palm seals, how the project started is that a utility provided us a data set to see what can you do with that, right? Can you tell me what's happening? And they have in that specific data set, they have like an erosion event and a normal data. So they told us like, okay, can you do something to differentiate when the erosion event is happening to normal data? And we were able to do that. So after that, like we say, okay, we have our test rig, we can simulate different failures. Like for example, we simulate again erosion, we simulate like wobbling of the shaft, heat checking, different things that can happen to the seal. And with that, we create like like signatures for each of the failures. We developed that tool, and then the station provided us a longer data set, and we tested that with our tool, and there was some success on that. One of we're still working on that because the data that they provide us was not very good quality. So again, data quality, and also most of it is normal data. They gave us like 2 weeks of data, and it was all normal data. So it's very difficult to test if you can identify failures properly when you would just have normal data. But yeah, we're working with utilities for that.
And I would just add one thing to that, we've been to multiple sort of conferences where the utilities come and present their different efforts in the area of AI and machine learning, like the DIET conference that I supported organizing. So they are implementing a lot of these technologies, but what they are using it for doesn't tend to be for like making decisions in the operating reactor, as I've seen so far, right? A lot of it is the low-hanging fruit of how can we make our operations more efficient or safer without, putting AI as like the main decision maker. So for example, I think it was OPG, they have like tablets around that are looking to see with video footage, and they're double checking if their workers have the appropriate personal protective equipment. And then if the image says like, "Boo, you forgot your helmet, like please go put your helmet on." So it's like an additional leader in the field reminding people to make sure that you have the appropriate PPE, which is great. It's just making things safer. It's not like it's not intercepting a signal or like telling a reactor how to behave. It's just trying to make the overall environment safer. Oh, yes.
I guess I have a very general question. Is there a way to, there must be a way to eliminate bad inputs, or tell the AI to ignore bad data? Like I just don't really know if that works, especially over time, or if it's not discovered until like later you've got this machine learning patterns of recognition that's happening.
Okay, so just to repeat that for the microphones, is there a way to eliminate bad inputs when you're trying to train a machine learning algorithm? I'm tempted to give it to you.
So you can look for outliers just statistically, but I think there still is a lot of curation, because if you have missing, like you can look for missing data too, or there's different things you can look for and just eliminate, but it's difficult to, and there are methods to look for anomalies in your data, but it's difficult if, the method is only as good as the data, and a lot of work goes into the data curation by a human, because you're trying to, well, I guess what you're saying is sometimes it's trying to like do what humans are doing faster, or but use the like the human expert to curate the data, and so that the machine learning algorithm learns the correct things. I don't think I explained that properly. But so there are machine learning methods to look for anomalies, and there are methods just from looking at outliers that you can drop certain things, but it can be hard to make you can get silly results. Like for instance, so I had an example, for instance, okay, so there's people who did scans of the heart, and they looked at, did the explainable method to see what part of the scan are you looking at when you're telling me this person has an enlarged heart. So and the scan was like, often the part of the heart, you can actually put to it, but the part of the heart was highlighted, which is great. But another part that was highlighted was the machine. Like, was it a portable scan or was it a hospital scan? So that kind of thing. It could be that what happened there is that when there was a portable scan, the person was more likely to be sick because the machine was taken to that person to check them. And so it could happen to a human doctor as well. Like if you're going out in the field and someone, you like if you're in a hospital, say in lower, more poor community, you might say, oh, this person's more likely to be sick or something like that. But there's bias that happens. So you might be training your model with bias. So that's what I guess sometimes that you have to have the human reasoning of, is this make sense? Or is it learning something we don't want it to learn? Like it often learns, like if they're predicting crime, it often learns that, there's prejudice against like who gets arrested. So it learns that. So that's why you do need a human in the loop sometimes for that. It's not like nuclear, but kind of.
I guess I'll just add, like in my case, it's more like a traditional like signal processing. Like we have to do all of like processing of the instrument signals for the tools to work properly and for the data to be manageable.
Yeah, I would say like I think that the most difficult part, like training the model, it could be really kind of maybe not fast, but like over a weekend or something like that. But the actual labeling part takes a lot of time. So like again, comes back to the quality of the data and the curation of the data. So if you put in something incorrect, if I've seen it actually, some of my image stuff, sometimes I've seen that somebody would label something wrong, but because of the way that it was training and learning, it realized actually that's incorrect, and it actually figured out that was wrong, that they put in. So it depends also on the model you use and what you're actually using to look for, and what it's using for training, and what it learned too. But yeah, I think we should spend just like the most amount of time always on the data that we put in so that we know it's right.
And it's also the maturity of the AI. I mean, I think there are methods now that do different types of learning that are trying to learn more autonomously in some sense, which is like trying to correct the data as it's learning, but I haven't got to that part yet.
Okay, any more? Oh, we got another question in the back.
Just sort of following up a bit on the question of data quality. Obviously, you've got data quality for learning, and then out in the field, you're going to run into poor quality data on occasion as well in application. So let's say you have a classifier ABC, right, and it's sort of sitting around and saying, well, it's mostly A, oh, now we have B, and then you run into some condition that's actually not like any of the conditions it was trained on, right? How do you handle that kind of event in terms of whether it's flagging a human supervisor or something to say, rather than, oh, well, it's closest to A, so I'll just call it A, to say, I have no idea what this is.
Besides explainability, another area of research is uncertainty quantification in machine learning. So ideally, it would say A, but with probability of 10% or something. So it would flag it to somebody else. And there's also issues with like data drift. So it might be that when you start off with sensors, they're a certain way, but then they age, and so the sensor signal changes as well. So I think this is like, I haven't had to deal with it in my day-to-day work, but those are, well, I'm thinking about uncertainty quantification, my day-to-day work, but I haven't dealt with that as much. But that's, I guess, two ways of addressing it. One is uncertainty quantification along with your prediction, and an explainability along with your prediction. Like, it looks like A because it's blue or whatever, and then a human person can say, well, it's not, and we don't care about the blue, or is the 10% is low for what I'm looking at. Or it could be like, I like things that even are a little bit likely to be, say, an accident, because I want to, I want to check those out even if they're only 10% likely. Yeah, but and then the second part is the explainability and the thing. Sorry.
I guess like for that, what you were saying about like a sensor drift, like we're working also in a project that it's about like a instrument signal validation. So it takes into account like the normal like wear and tear of sensors, but also when something is happening out of the ordinary. And the way that it does it is like by relating the information that one sensor is giving you to other parts of the process. And it's highly explainable because you need to learn to understand the process and see how the signals are related in between, and that way you validate your data before you feed it into a model.
Yeah. Yeah, to add on to what they've said, essentially AI is our tool, so it should only be used within the scope that we trained it and we know it can perform on. So if we try to apply, an AI tool that's used to find the layers in a triso particle to identifying, which is it a dog or a cat, it won't perform very well at all. So essentially, if there's something that happens that we weren't expecting that model to kind of know what to do with, it may give you a very weird answer. It's similar to what people are talking about with like hallucinations with ChatGPT and stuff. It's like you start going down a path, and at some point it's just making things up. But I do think it would be really good if it told us if it's making things up, like you're saying. So then I can be like, okay, I don't need to listen to you. I don't need to go down this crazy path. But yeah, that's my 2 cents on that. Thanks.
Good. You have questions? Okay. All right. Oh, we go.
Yeah. So this isn't actually me related, but I just became aware of it today. You've seen the QR code outside. Industry Science and Economic Development Canada is running a national consultation process around what the priorities should be for Canada's AI strategy. It closes tomorrow. So I just found out about it yesterday, and it just kind of popped in my head, hey, this audience might be interested in that. So it's just on the vote for it. Just on the door. Yeah, so there's a QR code over there, and the website. But basically, if you go to ISEC Canada's like survey at that link, you can just kind of put in your thoughts about priorities, and it's very big picture stuff, right? Ethics, access, the economic aspects, but everything else as well. So it's only been running for October. They're probably not going to get a ton of comments, so that probably means yours will be having unusual weight if you put one in. So it's a good time to kind of have some input in the national strategy in this area.
Okay, excellent. All right, well, thank you so much for having us. Thank you to the Deep River Library again and Naomi for the opportunity. Thank you to Bolu Bellu for supporting all the organization, our comms officer from CNL. Thank you to the audience for all of the lively and interesting questions and for your attention. And of course, thank you to our wise and established speakers and our excellent scientific communicators from CNL. Thanks, Catalina, Rosa, and Reeghan. So thank you so much and have a wonderful evening.